This is a brief introduction to probability. Let's just define a probability. The probability of event A is the number of A over the total number in the sample size. These vertical bars are referred to as the cardinality of the set. And let's define our set. Use curly brackets. Let's do 1, 2, 3, 4, 5, 6. And let's call event A, I don't know, even numbers 2, 4, 6. So we can see that the cardinality of S6, cardinality of A is 3. So the probability of A is the number of A over the total number of S, which is 3 over 6, which is equal to half. So let's have a look at some rules. So sometimes we refer to the rules of probability as axioms. A axiom is a fundamental principle which you can use in a proof. So the first axiom is that a probability of an event is non-negative but less than 1. The probability of the sample size happening is going to be 1. Let's do an example. Probability of head plus the probability of tail. Well, it's going to be half plus half, which is 1. And that is your sample size. Number 3, the probability of some disjoint events. This is referred to as or, and this is and. Okay, so disjoint events are these. And let's give a quick example. Let's have a look at the numbers between 1 and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say that this is even. Let's say that this is the number 1, and that is number 9. Well, even is going to be 2, 4, 6, 8, and 10. Which is 1, 1, and 1, 9. Well, the probability of getting an even is going to be half. Probability of getting a 1 is going to be 1 over 10. Probability of getting a 9 is going to be 1 over 10. So the probability of these events, we're just going to add them together. Half plus 1 over 10 plus 1 over 10 plus 5 over 10 plus 1 over 10 plus 1 over 10 is 7 over 10. Okay, so disjoint events are not independent. They're different scenarios or in different dimensions. The only way disjoint events can be independent is if the probability of the other disjoint event is 0, and we refer to that as trivially independent. Okay, so let's have a quick look at this example to define a conditional probability. Okay, so we need a probability of a win. Is the sample size of the win over the total sample size. This is sometimes called the event space. This is called sample space. So let's have a look at the probability of a win. We can count the wins there. 1, 2, 3, 4 over 8, which is half. And we can go through the sample space and have a look. We need 3 tosses and at least 2 come down as heads, at least 2. So there, 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 there. 1, 2, 3, 4. Okay, so let's look at a conditional probability. The first coin was just tossed and it came down heads. How does this affect your chances? Okay, so let's call this E. The first coin came down and it was heads. So it could be this one, could be that one, could be that one, could be that one. So we have heads, 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 tails, heads, tails, heads, and heads, tails, tails. Okay, so if we know the first one, there's 2 chances of the second one, there's 2 chances, so we should have a sample space cardinality of 4, and we do 1, 2, 3, 4. Now let's work out the probability of a win given that the first coin is a head. Well, let's look at this in terms of sample space. Okay, so we're in sample space E, and we need a win. So the cardinality of sample space E is 4. At least 2 heads. 2 heads, 2 heads, 2 heads. So there's 3. So the conditional probability of a win given a head is 3/4. And we can write a little rule. Probability W given E is cardinality of reduced event space divided by reduced sample space. Okay, and that concludes our introduction.